All right, so we're still continuing our limits under the graphical understanding. But after we've learned and hopefully thoroughly enough throughout the explanations of how our graphical interpretation of the graphs explain our limits results back in the examples I offered in my earlier lecture, then once we've learned through those, let's apply our understanding of our understanding in terms of the graphical behavior of our function, of any function, into estimating an actual limit. So to really explain what I mean here, let me fire up an actual example where we're going to apply our graphical understanding of any function into estimating its own limits. So now I'm going to call that example 1. So let's say I'm going to have a worded instruction here. I'm going to let some function f of x, let f of x have the graph as given. Okay, so what graph is this? This is the graph of our f of x. So feel free to pause the video and take notes for yourself. And you can use your, in these high technological days right here, then you can go ahead and pull out a cell phone and or like some kind of phone and take a Photoshop of that. You don't need to make the exact duplicates, but we're going to be learning a lot about this function, and you don't even have to worry about what kind of function. Is that an x squared? Is that an x cube? It's just some function that it already had a graph given here right in front of you. So try to replicate the graph as close as you can, but doesn't have to be precise. And now I'm about to get started. All right, so hopefully you had a Photoshop of your own graph right there. Now I'm gonna get back into our double screen right here. So starting out with, we don't have to know what the function is again, but I know that our function has the graph as you already seen in my corner of the board. So maybe let me put this a little smaller scale this time so we can see it a little, everybody can see it a little better. But so here's the thing. Question A, how's that? Let's find, so trust me, after we are through with this example, everybody's going to be shocked of about how much we can learn by estimating a limit based on the graph right here. So let's say I want to find the limits of this function, f of x, by letting x, so f of x is simply given to us as the graph there, and you have already seen the graph, and the graph is still here on the screen. Let's find the limit when x is getting close to -6. Okay? And so -6 is our limit point. And let's look on the graph right here. -6 on the x-axis is right here. Okay? But then the problem wanted us to get close to -6 on the x-axis, generally from both sides. So now, once again, that is our responsibility to first consider the limit from the left-hand side, and again, consider the limit from the right-hand side of -6. So now I'm going to use my mouse cursor right here to trace along the graph. But as I'm coming closer to -6 on the x-axis, then the graph drops down to, it looks like, well, we can, estimating through graphs, the best thing we can do is just to rely on our own the eye judgment. So I'm looking at, by using our sense, our visual sense, I'm estimating that the height, the limits here, drop down to about -2. But I'm getting close to -6 from the left-hand side. So this is our main target of the problem. But let's work it out a little bit. So since the limits from the left-hand side, coming to 6 from the left-hand side, it looks like it's -2. And quickly, let's do another one. On our screen here, we're getting closer to -6, but from the right-hand side. So observe my mouse pointer motion again. that as I'm tracing along, you can see that my mouse is getting closer to x equals -6, but the vertical height keep making its way to drop down to -2. And so I can also say that on this function, as we're looking at the limit, when x getting close to -6 from the right-hand side, that limit also appears to be 2. And so left-sided limits and right-sided limits agree, so that means our final answer here has to be a -2. Okay, so that's how we answer part A. And now in the later problem, I'm going to start picking up pace here a little bit. Allow me to erase these finished work. So what about let f of x have the graph as given. Okay. So how about in part B, same function. Let's consider the limits of the function when x is getting close to, let me see, -2, but from the left-hand side. Let me rewrite that. Let me correct my writing here. I'm letting x getting close to -2, but from the left-hand side. So once again, the problem is asking us to understand that -2 is our limit point. Okay, but we're getting close to -2 from the left-hand side. Okay, so getting close, -2 on the x-axis is here. Getting close to -2 from the left-hand side means we're going this way. That means if we're tracing along our graph right here, I just now remember that the decimal has this feature that I can click and hold down and drag, and then that's how it's tracing along. So as I'm getting closer to -2 from the left-hand side, then it looks like I'm approaching that height being estimated about 2 right here. Now don't worry about that empty point. I'm not really having a point here, so don't worry about the empty point, but the idea is as I'm getting closer to -2 from the left-hand side, it looks like I estimated that the answer here is estimated to be 2. And see, so how critical that is, it is to understand that we will never plug in, because here if we are substituting x equals -2 into the function, maybe let me bring that into another question. How about question C right here? This same function f, question C of example 1, if we're substituting -2 into the function, what is our value? We have an empty dot. The empty dot is right here. And so as a matter of fact, in formal algebra term, this is an undefined. So we have a nice mix of all kinds of problem in this graph given right here. F of -2 has an undefined value, but limit of f of x when x getting close to -2 from the left-hand side is a 2. Okay, because the height is just a height. So all these graphs here from the left-hand side, as we trace along the graph, it seems like the height is getting higher and higher and about to get close to that height being 2. Okay, and so now I can produce another problem. How about question D right here? Same function. How about getting close to -2, but generally from both sides? Okay, same function, same graph that you're still currently having on screen right there. But here I'm looking at, let's find the limit of this function f of x as x getting close to -2, generally from both sides. So let's utilize what we have already done. We already found that same function here, same graph here. If we get close to -2 from the left-hand side, our answer was 2. Okay, and so now the only other responsibility we need to start getting into here is f of x, and consider the limits when x getting close to -2, but from the right-hand side. The problem did not ask us for that, but it is our responsibility to understand that we have to have two separate sided limits completed before we can make our final conclusion. So here, as x is getting closer to -2 from the right-hand side on the x-axis. So let's trace along and find out what's happening here. So as x, now I'm tracing along my graph here, and now if I'm getting closer to -2 from the right-hand side, it seems like my graph is also gaining height and gaining height, and it seems like it's making its way to attempt that vertical height 2 right there. Okay, so I can also make conclusion that the limit of this function given as a graph, when x gets close to -2 from the right-hand side, it has limit 2 again. And so now this question here that we are ultimately asked for, this limit when x comes to -2 from both sides, the function comes to limit +2. And again, recall, I hate to repeat what you have done, but recall for yourself in part A that f of -2 was undefined. We have an empty dot, okay? But limits, there was an existing value. So critically remind yourself, and I did mention this since very early the lecture, since the earlier lecture, that anytime taking limit, it is strictly to remind yourself that we are not plugging in the limit point value into the function, because sometimes, a lot of times, the tricky problems come out like this. Substituting in or plugging in the limit point value gives you an undefined, but taking limits can still be done. Okay? And so let me continue further into this example. All right, and so once again, f of x is some function having graph as given, and you are still seeing it on screen right there. Part E. Okay, part E. What about, let's look at this. So f of x, but I want to find out what's the limit of f of x when we're coming closer to 1 on the x-axis. And once again, I'm doing two-sided limits here. So I want to find out the limit of this function as I'm letting x getting close to 1, but generally from both sides. Okay, and so once again, it is our responsibility to tear this down to two separate approximates or two separate estimates from the left-hand side. F of x, we're going to have to consider this separately. X getting close to 1 from the left-hand side. What kind of limits for f of x that we can estimate here? So 1 is right here on the x-axis. So now as I'm tracing along, you can see that my mouse is getting closer horizontally to 1. But as I'm tracing closer, then the height seems to attempt to -1. So from the left-hand side, my function here comes to limit -1 as x comes to 1 from the left-hand side. And then we're going to have to consider what that limit would be for f of x when we're getting closer to 1, but from the right-hand side. Okay, and now on the right-hand side, it's a pretty unusual piece right here, but as I'm tracing along the graph right here and coming closer to 1 from the right-hand side, and it looks like the height dropped, but drops to +1. So this limit now is +1. So left-sided limits and right-hand-sided limits do not agree. So here is another example where we graphically estimated that this function here, when x gets close to 1, this function has a DNE limits non-existing, does not exist limit. Okay? And now let's look into the next example. Actually, I mean the next part of this current example. So we finished with part E. So let's now look at part F right here. About let's find limits of this function f of x when we are letting x getting close to 3. Okay, and once again, the problem is looking for the general two-sided limit, and so it is assumed to be our responsibility that we have to be able to do a left-hand side limit first. So f of x on this same graph, I am going to trace along the graph as I let x coming close to 3 but from the left-hand side. Okay, and let's find out again. So tracing along, it looks like when I'm getting closer to 3 horizontally and tracing along the graph, horizontally my mouse is getting closer to 3, but my vertical height is keep rising and rising and rising. And so here I can say that I'm reaching to a positive infinity for y output, for f of x output, as I'm getting closer to 3 from the left-hand side. And then now I'm going to turn my focus, my attention over to finding the limit of the same function, f of x, but now considering the x value getting close to 3 from the right-hand side. And then once again, that tracing work here is going to start coming back again. I'm tracing along my graph, and as I'm tracing along my graph here, my x value is getting closer to 3, but my y value keep rising and rising and rising. And so now I can conclude that the limits for x getting close to 3 from the right-hand side on this function is also going to grow to positive infinity. So two-sided limits agree this time, but to a sort of like a direction, a growing up direction right here. So this limit in general can be concluded that generally from both sides, as x getting close to 3, our function comes to limit positive infinity. And that's how we're answering it. Okay? And of course, we can have a lot of other problems here. I'm about to run out of my own creativities with these different examples you can create. But the idea is, once again, once you understand the graphical nature of your own function, then we can answer and understand how the graphical nature of your function explains the limits. Then we can answer a lot of these limits problem by estimating through the graphs. How about one more problem? What about f of 3? This is substituting it. This is plugging in the value 3 into the function. Can we really get this value? No. The graph is right here. It's, as a matter of fact, it's having an asymptote, or it's asymptotic in our formal math term right here. So we have an undefined value. So f of 3 equals undefined. So anytime we're substituting in and fail to have a value, we call that situation we're having an undefined value. Whereas anytime we fail to find a limit, we call that it's a DNE. It's a non-existing, does not exist limit. Okay? So our value here is being undefined. And now another one. About this question H right here of our example. Same function, but what about f of 1? Okay. Now remind yourself, we did earlier, I can't at this point I can't remember which part that was anymore, but we did find this limit of the function as x getting close to 1 generally from both sides. And recall for yourself, if you took note, that this limit was a DNE. So we did not have a limit when x getting close to this limit point. But what happened if we're substituting in, if we're plugging in the value? See, so I keep emphasizing that it's entirely two different works. One work is substituting values in, the other work is finding limits. So we're substituting values near this limit point, but we will never substitute that direct point, limit point into the function. So having a DNE here is different thing with substituting 1. So substituting 1 into the function. Let's say when x really is equals 1 in the function, we do have a solid point down here on my graph right here. Okay, and the solid point is at coordinates, the y coordinates -1. So our output value in this case is actually -1. So here's another case where you see, limit is a non-existing limit, but the actual value is defined. We're having a finite function output value, and I believe this question H right here, this question H right here concludes our example 1. But here's my next plan right here. I am going to design example 2, but I'm more gonna write down the problem and for viewers to do the work on your own right here, and I'm just simply gonna give the answer without any further explanation because I need you to be able to carry this on your own right there. So very same example, very same kind of example. Let's look at example 2 right here. So I'm gonna start out with having some function f of x with the graph as given, but allow me to switch to a different graph. So here's our graph of this new problem right here. Okay, and for one moment, allow me to how about show that in full screen right here, so you can see that a little better before I put that into a small little corner of the screen. Okay, so here's your graph, and have a good nice view of that, and then I'm gonna turn that into, I'm gonna put that back into just its little corner of the screen right here. But now I'm gonna start putting question at you, but keep in mind the plan for this example I'm about to do here. I'm only gonna write down the question, and I'm leaving it for you to find the answer. And once I write the answer up here without any of my explanation, then I need you to confirm whether you had agreed your answer with me or not. And if you don't agree with if for any reason that your answer doesn't agree with mine, feel free to contact me in person for explanation. So, question A. So remind yourself, this is for you to try, really, pretty much for you to try. So with the function f of x having the graph as given there, then what about find for me the limit as for this function f of x as x is getting close to -3. All right, so go ahead and pause the video and get yourself some tracing work and find out what that limit is. Okay, so hopefully you're back now and having your own answer. The answer here is a D and E. Okay. And like I said again, allow me not to give the reasoning. If you would like to look for reasoning because my answer doesn't look like your answer, feel free to contact me. What about part B? I'm going to put up a different questions regarding the same graph. So in this same graph, question B, what about find for me the limits of this function f of x as x is getting close to 3, positive 3. And once again, pause the video, have some thinking for your own, and then once you're done, go ahead and resume with the video. Okay, so my answer for this problem is 1. And that is my answer. And once again, feel free to contact me in case your answer did not agree with mine. And here we are at the next question. So what about on this function f of x, find for me the limits when x gets close, limits of f of x when x gets close to 6 from the right hand side. Right. All right, so hopefully you had your own answer. My answer is -2. And let's keep going further. So how about question D? Same function, f of x. Let's find the limit when x comes close to 6. Notice, no special superscript indication. All right, go ahead and find your own answer. And now my answer is -2. And another one. Okay, question E is here. So let's say I want to find the limit of my function here as x is getting close to 0. I mean, I apologize. About -1 actually. All right, have your own answer. Okay, and here my answer is, as a matter of fact, D and E. That is my answer. And once again, it starts feeling a little antsy because I keep moving on and throwing the final answers at you, but without any explanation. Like I said again, my intention of this example, the way you're doing it, is exactly like how I have done back in example 1. But feel free now if your answer doesn't agree with my answer. Okay. All right, and last one for this example. What about f at 6? My answer is simply +1.